In the previous video, we had an introduction to solutions, some of their properties, and some definitions. So we're going to continue that discussion in this next video. First question is, how do we know whether a solution is going to form in the first place? Some substances are mutually soluble and some are not, and there's some basic rules that will let us make predictions about those. For example, is carbon tetrachloride and water, is that a soluble combination? Well, at this point you probably have no idea. But it's insoluble. For reasons we'll talk about in a moment, carbon tetrachloride and water will not dissolve in one another. How about ammonia and water? Turns out ammonia is actually very soluble in water. They dissolve quite nicely. Salt and water, probably no surprise, you're all familiar with that. That is clearly a soluble combination. And carbon tetrachloride and iodine. Now that's probably a couple of things you're not extremely familiar with, but those two substances happen to be quite soluble. So the question, of course, is why? What determines whether something will be soluble in a particular solvent or not? The reason that certain substances will dissolve in other substances has to do with the types of compounds they are. Whether they're ionic compounds, polar covalent compounds, or nonpolar covalent compounds, the overall rule in chemistry is like dissolves like. Substances prefer to dissolve with another material that is similar to them. So it's not like the opposites attract things you hear sometimes. In the case of solutions, it's like dissolves like. So let's see why that's the case with each of these four. For example, water and carbon tetrachloride. Water is a polar molecule. In fact, it's got hydrogen bonding, so it's very polar. So water has fairly strong positive and negative poles. Carbon tetrachloride, because it's tetrahedral, is balanced and nonpolar, so it does not have those nice positive and negative charges, so water isn't very attracted to carbon tetrachloride. It's not that water is repelled from carbon tetrachloride, it's just that water likes other water molecules better. The positive and negative poles between two water molecules will attract each other. So the water molecules, is not that they don't like carbon tetrachloride, it's simply that they love each other. They get much stronger bonds if they simply stay together, and so these substances simply do not mix. And therefore we would call this an insoluble combination. Okay, the next pair we looked at was water and ammonia. Now ammonia is a polar molecule like water. In fact, they both have hydrogen bonding. So there's a strong attraction between water molecules and ammonia molecules. And therefore ammonia dissolves in water very nicely because water loves water, but it also loves ammonia. And so it can do just as well bonding with ammonia as it can with other water molecules. And therefore, this pair is a soluble combination. Like dissolves like. Polar goes with polar. The next example we had was salt and water. Now, of course, water molecules attract each other, but they're also very strongly attracted to the positive and negative ions in sodium chloride. The hydrogen end of the water molecule is attracted to the chloride ions, and the oxygen end of the molecule is attracted to the sodium ions. This is true with any ionic compound, not just salt. And because of those attractions, ionic compounds like salt, if they're going to dissolve in anything, it's going to be a polar solvent like water. Ionic compounds don't dissolve in nonpolar substances like carbon tetrachloride because there really just isn't a strong enough attraction. But the attraction between ions and water is very strong. Okay, the last one we talked about was carbon tetrachloride and iodine. Now these are both nonpolar molecules. Of course, a single element will always be nonpolar, and carbon tetrachloride, it's balanced. The chlorines are all balancing each other out. So these molecules only have what's known as a temporary dipole. So as we talked about in chapter 14, as the electrons are moving back and forth in the molecule, they can momentarily form positive and negative poles. So the carbon tetrachloride molecule can temporarily become polar, so can the iodine. And so for a moment, the two attract each other, then the attraction is gone. Then they get that temporary attraction, it's gone, comes back, gone again, and this goes back and forth. So there is at least a small amount of attraction between nonpolar molecules. Not enough to interest a polar molecule. A molecule like water's not real interested in a molecule that's only polar some of the time. Water prefers to dissolve with something that's polar all of the time. And so two nonpolar molecules like carbon tetrachloride and iodine will dissolve together very well. So let's just summarize the rules then. First rule is polar solutes dissolve in polar solvents. Like dissolves like. And of course, logically then, nonpolar solutes dissolve in nonpolar solvents because again, they are like each other. And then our final example is ionic substances. An ionic solute will dissolve in a polar solvent because they actually are alike. Ionic compounds have positive and negative charges. Polar covalent molecules also have positive and negative charges. What I mean by the degree of solubility is simply a measure of how much solute can dissolve in a particular amount of a solvent. For example, we can't dissolve 5 pounds of sugar in 200 grams of water. If we try to do that, we'll simply end up with wet sugar. So even though sugar is soluble in water, there is a limit to how much you can put in there. Now, on the other hand, if we had 5 ounces of sugar and 200 grams of water, that would work. The sugar is pretty soluble, and we would be able to dissolve that amount of sugar with no problem. So all substances have a certain amount of solubility. Some things are more soluble than others. Sugar, for example, at 20 degrees Celsius, about room temperature, is quite soluble in water. You can put 408 grams of sugar in a mere 200 grams of water. Now, of course, there's a reason I put a temperature here, because solubilities do depend on temperature, and we're going to talk about that a little more later on. If we increase the temperature to 50 degrees Celsius, the solubility rises to 520 grams of sugar in that same 200 grams of water. Now, each of these solutions represents the maximum amount of solute that you can put in a particular amount of solvent at a given temperature. Both of those solutions are described as saturated solutions. A saturated solution simply means that the solution contains the maximum amount of solute possible. If I put 409 grams of sugar in 200 grams of water at 20 degrees Celsius, I could still only dissolve 408 grams. The other gram of sugar would simply sink to the bottom, and you'd see a little bit of sugar crystals on the bottom of your container. So, at 20 degrees Celsius, if we put 408 grams of sugar in 200 grams of water, we have what's known as a saturated solution. Now let's suppose that we heated the solution up. We take this exact solution and we heat it up to 50 degrees. Is our solution still saturated? Well, according to our information up here, we have room for 520 grams of sugar, but we've only got 408. So we have less than the maximum amount, and therefore this particular solution would be called unsaturated. Now let's continue on. Let's go ahead and take this warmer solution at 50 degrees and add another 112 grams of sugar, bringing it up to a total of 520. If we do that, we now once again have the maximum amount of sugar that you can dissolve in 200 grams of water at 50 degrees Celsius, and so we're back to being saturated again. So saturated is a different amount depending on what your temperature is. Now, For our final step, let's cool the solution back down. Let's lower the temperature back to 20 degrees Celsius. At this temperature, there should only be room for 408 grams of sugar, but we have 520. What should happen immediately is the extra sugar should all crystallize out. We should very quickly find 112 grams of sugar crystallized in a pile on the bottom of the beaker. With most chemical compounds, that's exactly what will happen. But that's not the case with sugar. That extra sugar is going to remain dissolved, and we have now what's known as a supersaturated solution. So a supersaturated solution is simply one that contains more than the maximum amount that's supposed to be possible at a given temperature. Eventually, that extra sugar will crystallize out. It just happens to take some time. Now there's a fun experiment you can do at home, especially if you've got kids, and that's making rock candy. So we can take advantage of this supersaturated property that sugar has, and we can slowly grow these really lovely crystals. So if you follow the link in the upper right corner, you'll be able to go to this video by the Sci Guys about making rock candy at home. If you have any trouble using that link, don't worry, I'm going to also post a link to this video on Canvas right after the link for the current video. There are a couple of factors that can have a pretty significant effect on solubility. The first one of those that we've talked about a little bit already is temperature. When we were talking about sugar just a couple of minutes ago, we found that temperature did have a pretty significant effect on the solubility of sugar. So for solids, the general rule is that increasing the temperature will increase the solubility. That's not always true, but most of the time. There are some rare exceptions where increasing temperature actually makes a solid less soluble, but that's very uncommon. So let's take a look at a hypothetical crystal of sugar. If we add that sugar to water, in order to get the sugar to dissolve into the water, we have to break the bonds between the sugar molecules. If the temperature is fairly low, then it's more difficult for the sugar molecules to break apart. It takes energy to break those bonds. So at a lower temperature, we're not going to be able to get as much sugar to dissolve into that water. On the other hand, if we increase the temperature, that additional energy helps to break those bonds, and now we get more sugar dissolved in the water. So for sugar and almost all solids, that additional energy helps to break the bonds between the molecules and allows us to dissolve more solid in a given amount of liquid. Now temperature also will affect the solubility of gases, but it's actually the opposite direction. Increasing temperature actually decreases the solubility of gases. And let's take a look and see why that is. When a gas is dissolved in water, the gas molecules, remember, are already separated from each other. That's the nature of gases. So when you have something like a solid like sugar, the first thing you have to do is break the particles apart. Well, in gases, that's already been done. So the gases can readily dissolve into the liquid, and the gas particles form bonds or attractions with the molecules of the solvent. In order for the gas particles to escape from the liquid, they need energy. If we keep the temperature colder, then it's more difficult for the molecules to escape. That's a good reason, if you're opening a can of Pepsi or Coke or whatever soft drink you prefer, if you keep it colder, it will remain carbonated longer. At a low temperature, it's harder for those carbon dioxide molecules to get enough energy to break the bonds with the water and escape. If your soft drink is warmer, then the molecules have more energy. So if you warm it up, now with that extra energy, it's easier for the molecules to escape into the air, and your carbonated beverage is going to go flat faster. It's the same reason that fish like trout and salmon like to live in cold water. In cold water, many more oxygen molecules dissolve in the water, which the fish need to live. In warmer water, if the water gets too warm, fish like trout can't survive. If it gets above, say, 70 or 75 Celsius, at 90 degrees Celsius, those trout would die. There is just simply not enough oxygen in the water for them to live. So it's the opposite of what we saw for solids. With solids, increasing temperature increased solubility. For gases, increasing temperature decreases solubility. The second property that affects solubility is pressure. Now it turns out with solids, they're essentially unaffected by pressure. Pressure has almost no effect on solids for a very simple reason. Solids already have their particles, molecules or atoms or ions, packed tightly together. So putting pressure on, say, sugar has no effect on it. The molecules are already touching each other. They cannot get any closer. So pressure really has no effect on the solubility of solids. On the other hand, it's a different story for gases. Gases are mostly empty space. So increasing pressure actually will increase the solubility of gases for a very simple reason. If we have a fairly low pressure, represented by just a few molecules of gas above our beaker, the molecules in the air are moving into the liquid and dissolving, but at the same time, gas molecules from the liquid are leaving. And they reach that state we talked about previously called dynamic equilibrium. Now, if we were to increase the pressure of gas, say we doubled the number of molecules of gas above the liquid, now they're entering the liquid twice as fast. So they're slowly going to build up more molecules in the liquid until eventually we get this balance once more. But because we doubled the pressure, once we achieve dynamic equilibrium, there's going to be double the number of molecules dissolved in the liquid. And so gases are more soluble at higher pressure, and solids are essentially unaffected by pressure. Soft drinks, as we mentioned earlier, are a good example of this. They put a lot of pressure of carbon dioxide above the liquid in the soft drinks. So all those CO2 molecules up above the Pepsi or Coke or Fanta or Sprite are hitting the surface of the soft drink and they're dissolving. And the more molecules you pressurize in that can, the more of them are dissolving in the liquid and the more carbonated it will be. Of course, as soon as you open the can, out comes the pressure and the molecules begin to escape from the liquid and eventually the soft drink will go flat.